This is section 14, optimization, example 4. So a manufacturer needs to produce a cylindrical container with a capacity of, this is actually a typo, that is supposed to be 1,000. No, you cannot just do that whenever you want. That was an actual typo, so keep that in mind. The top and the bottom of the container are made with material that costs 5 cents per square centimeter, while the side of the container is made of material costing 3 cents per square centimeter. Find the dimensions that will, lots of typos, minimize the company's cost of producing the container. So, first let's figure out what formulas we're using. All right, so it tells us that the volume is 1,000 cubic centimeters, right? So that's the capacity. The capacity is the volume. So I know how to find the volume of a cylinder. It's the base times height, okay? And the base is a circle, so it's pi r squared times height. So the volume, which is 1,000, is pi r squared h. Then it says that the surface area is giving us the cost, essentially. So the cost, that's C, and we want to minimize the cost. Okay, so that's how we know this is an optimization problem. I told you, see, it could be minimization. But to do that, we are going to have the cost, which is 5 cents for the top and the bottom. So 0.5 times the top and the bottom, and that's the surface area, so it's pi r squared, plus 3 cents times the, the side of the container. And it tells us that the lateral surface area is 2 pi r h. So 2 pi r h. Now, it's the cost that we're trying to optimize, which means that we need to take this equation over here and solve for a variable to plug in. And it might be easier, because we have h once, to just solve for h. So h is 1,000 over pi r squared. So let's take that and plug it in over here. So C, and I'm going to go ahead and simplify a little bit as I go. And actually, I'm sorry, I messed this up. It's not pi r squared, it's 2 pi r squared, and it's two of them because there's a top and a bottom, right? So 2 times 0.05 is 0.1 pi r squared, and then 2 times 0.03 is 0.06 pi r, and then h was 1,000 over pi r squared. Now I can simplify some stuff. I know that pi and r go away, so there's only one r. And this is going to end up being the equation that I end up optimizing. So, let's see. C equals 0.1 pi r squared plus 0.6 times 1,000 is 60, and the r was on the bottom. Now, I take the derivative, set it equal to 0, and solve for r. So C prime is 0.2 pi r, and then the derivative of 1 over r is negative 1 over r squared. So it didn't affect the 60. And that's going to equal 0. So the way that I'm going to do this is get a common denominator. And right now r squared is in the bottom of the right one. So I'm going to multiply by r squared over r squared. So this equals 0.2 pi r cubed minus 60 over r squared. And to see where this equals 0, I would take that and set it equal to 0. So the numerator. So 0.2 pi r cubed minus 60 equals 0. So 0.2 pi r cubed equals 60. I'm going to divide by 0.2 pi. So r cubed equals 300 over pi, and r equals the cube root of 300 over pi. That's the r value that will minimize the company's cost. We need to now find the height because it's also asking for the dimensions. So the height ends up being 1,000 over pi r squared. I'm just going to go ahead and plug it in and tell you what number I get. It's 15.236. And when you optimize the cost actually ends up being I'm plugging in 300 over pi. The cost ends up being $19.69.